In the last lecture, we started the concepts of Bode plot. Although the idea of Bode plot and the mathematical foundation for it is relatively straightforward to understand, it is also very important that you understand what a Bode plot represents. To make sure that this is very clear, let's consider this example. We have a DC motor that drives a inertial load. The DC motor takes an input V, which is a voltage, and the output here will be either the speed or the position of the output shaft. For simplicity, we are going to neglect all the electrical properties of the motor. We are assuming that a voltage gives a torque to the load, and that relation doesn't have any delay or any transfer function between them. It's simply a gain. Of course, we know that that assumption doesn't hold true, but this is just for simplicity here. Let's assume that this motor is actuated with a voltage V that we are going to here choose to be a square waveform. We're going to apply V to the motor. Let's call that a V1, the magnitude of that input. We're going to hold that voltage at a constant value for a certain period of time, and then reverse the voltage to negative V1 and hold that for the same amount of time before again we switch to back to V1 and so on. What happens to the motor? Well, if you turn the motor on by applying V1, the motor will start to spin in one direction. When you reverse the voltage, the motor starts to spin in the opposite direction. Easy. Let's call this time here T1, and let's call this time here T2. What is the frequency of this signal? The period is T1 plus T2, so the frequency here is 1 over T1 plus T2. So the greater the period, the lower the frequency, the more time the motor has to spin in one direction and in the other direction. The lower the period, the higher the frequency, the less time the motor has to spin in one direction before it has to switch to the other direction. Very well. Now let's attempt to draw a Bode plot of this that represents the output speed. Let's just start with the speed that I'm going to call here omega. If in this case T1 is sufficiently large, what happens to omega? Omega will start to increase and the motor will reach a maximum speed and then will spin at that constant maximum speed. So if T1 is around here, we give the motor sufficient time. We're assuming again that T1 is enough time for the motor to now speed up and reach that constant maximum speed. That constant maximum speed we are going to call here omega 1. So this is omega, the omega of T, the speed of the motor. What happens at T1? Well, at T1 we reverse the voltage, so the motor now starts to spin in the opposite direction. And again, T1 and T2 are the same here. So now the motor will reverse speed and eventually reach negative omega 1. Once at T2, we reverse the voltage again. So the speed of the motor will now go up and reach again the same value and so on. And now it goes back down and this cycle continues. The assumption once again is that T1 is sufficiently large to let the motor reach that maximum speed. And we reach the speed omega 1. Now we can attempt to draw some sort of pseudo Bode plot that will show how omega 1 will change if we change this frequency, if we change the amount of time the motor has to spin in one direction or the other. We can now make a second plot where now the horizontal axis is the frequency. This one will also be the frequency, not time. And this axis is now the maximum speed we reach. If we are here at a frequency f1, and put it say here, we are going to reach a maximum speed of omega 1 right there. What happens now if we decrease the frequency? If you decrease the frequency, we are given more time for the system to spin. So this entire diagram is basically stretched to the right. T1 increases, T2 increases. Everything again expands to the right here. What happens to the maximum speed? It doesn't change. We are simply giving the system more time to develop the speed, but the speed will eventually go up and stay at that same speed. Alright, so even if T1 shifts to the right, the motor will go up and reach that maximum speed. So if we decrease the frequency, let's call that frequency F0, we reach the same maximum speed, omega 1. And if you keep decreasing the frequency, the same happens. You're just giving more time for the system, but the final value doesn't change. It always reaches omega 1. Now what happens if we increase the frequency? If you increase the frequency, we are now changing the voltage more often. Say in this case here, twice as fast. Let's call this frequency here F2. What happens here? Let's assume that F2 doesn't give the motor sufficient time to reach its maximum speed. So when you turn the motor on, it will start to go up. And when you reach now your new time here where we reverse the voltage, we will stop there and the motor will now go down in the speed and go in the opposite direction. We now reach here, this point, where again we switch the voltage and now the speed reverses. So now the speed goes back up and back down and back up and back down and back up and so on. We notice here that we reached a different value for the final speed. Let's call this value omega 2. Clearly, omega 2 is smaller than omega 1 because we are giving the system less time to develop a speed, and that time is not sufficient for the motor to reach its full speed. We are now going back and forth. So the motor, of course, the less time we give for it, the higher the frequency, the lower the maximum speed we reach. So now if you go at frequency F2, we will see that will start to decrease. And if you go now to a frequency F3, where F3 is greater than F2, that will further decrease. Here we have our omega 2. And you can see that this approaches the gain plot on a Bode plot. We have the magnitude of the output past F1 will now start to decrease. We assume that F1 is exactly the cutoff frequency of the system. Past that, now the system doesn't have enough time to develop the full speed, and the higher the frequency, the lower the gain. Why is this flat? Well, because if you decrease the frequency, we are simply giving the system more and more time, but it doesn't matter because you always reach the maximum speed. Hence this flat line. Very well. Now let's look at position, theta. Let's plot theta of t here. Same idea. We'll first look at the green line here. Well, to me it shows as green. I mean the first one I have, the one that we use for F1, given here. We turn the motor on up to a time T1 with voltage V1, and then from T1 to T2 we apply negative V1. What happens to the position? Well, the position, here we have T1, here we have T2, we will start to increase. After a certain transient, it will go up like that. And when you reach T1, now we will start to decrease and back up and back down and back up, of course with some transient. Let's assume that at this maximum position here that it reached, it was theta 1. We can now plot our function here, F1, the frequency, and the maximum position, let's call that theta 1, and this is negative theta 1. Here we are. Now what happens if you give more time for the system to develop its position? If we decrease the frequency, we again are increasing the time. T1 and T2 become larger. What happens to the position? Well, the position will keep increasing. Unlike the speed where we reach a maximum value, if you give enough time or more time to the motor to develop a position will keep increasing. So if the frequency decreases, this will start to go up and you keep going up. Because once again, the lower the frequency, the greater T1 and T2, the more time the motor has to spin in one direction or the other before it reverses direction. And position will always start to increase. So if you give it an infinite amount of time, that is, the frequency tends to 0, T1 and T2 tend to infinity, then the maximum position also tends to infinity. What happens if you increase the frequency? Well, we'll keep decreasing the maximum position we reach. Because now we are simply doing the same that happened to the speed. Something like that. And this maximum value here, we'll call that theta 2, negative theta 2. So if you are at a frequency f2, then this will further decrease. And this will decrease now at a faster rate. And this faster rate will come from the fact that we just crossed the limitation here of f1, which came from the fact that we have inertia and friction. If you now pass the frequency where we started to see the decay in a speed, the position will decay faster than before. So this slope will also change. Now we had one slope here, the slope will become steeper because now we are at that famous frequency f1 where we started to notice that past that point the system doesn't have enough time to develop its full speed. If we now take the integral of the speed that is reaching a lower and lower value, the position will result in a lower and lower value as well as we start to increase the frequency. So this slope now is a combination of the inherent slope that we see in the position that always goes up when the frequency decreases, plus the additional slope that comes from the mechanical characteristics of the system. This cutoff frequency here comes from the fact that our transfer function in this example would be the torque divided by Js plus B. We see a real pole, the real pole that we assume to be placed around this frequency f1. So now here we have the addition of, again, that inherent behavior of the system that keeps increasing the position if it has enough time, plus now the cutoff frequency that you see here that is affecting the speed. Now let's try to compare these two graphs. This is speed, which is taken from this transfer function. This is position, which is taken by integrating this transfer function. Right, the output here is, the input is torque, the output is the speed. We see here a flat line. We understand why we have a flat line here, whereas here we have this slope that keeps going up. Where is that coming from? Well, here we have speed. If you want to go from speed to position, what do? We have to integrate it. And by doing this integration, we are actually multiplying this function by 1 over s and adding a pole at the origin. This pole at the origin adds this slope that is now constant throughout the entire frequency spectrum. And that's why now the slope that was 0 became non-zero here. We know that this is negative 20 decibels per decade. This slope just increased. It increased because we had the effect of the inertia and friction that resulted in this cutoff frequency, which is again there, but now in addition we have that slope created by the pole at the origin, which is the integration of this reflected there. And this now represents the Bode plot, or something that could be a Bode plot with further manipulations, which is the frequency response of this particular system. The difference is that, first of all, we are not using a square waveform in a Bode plot. We use a sinusoidal waveform. So all these waveforms that you see here are also sinusoidal. I chose to use a square waveform here just for simplicity, so it's easier to explain and easier to visualize. But in reality, this is a perfectly sinusoidal waveform. But it doesn't change the understanding of the concept. The second difference is that here we are actually doing 20 log of omega and here 20 log of theta. Now notice something else as well. Here in this transfer function, the magnitude of the input is already there. If we change the magnitude of the input from V1 to something greater than V1, what happens? Well, the magnitude here and here will increase, so the entire Bode plot will shift up. If you decrease the input magnitude, so we say like half of V1, then everything will shift down. Right? And it makes perfect sense. If we increase the voltage, the motor will spin faster. If you decrease the voltage, it will spin slower, so the maximum position and speed that it reaches is smaller. And that's a representation of the Bode plots. What can we conclude from this? Well, you'll notice that when you buy motors, when you buy electrical components for your robotics or mechatronics projects, they will all come with a Bode plot. And they are there for a reason. The reason is that their Bode plot tells you at what frequency those components will operate. Imagine that you want a robot to do some sort of pick and place task. And you want that to operate, that a pick and place will occur at a frequency of, say, 10 Hertz. If your cutoff frequency here is too low, say 1 Hertz, then you will have to increase the magnitude of the input by a very large amount in order to get the displacement you want at the output, the magnitude of that displacement or speed at that particular frequency. If your cutoff frequency happens to be at, say, 50 Hertz and you want to operate at 10 Hertz, then if you look at speed, you are fine. Within that range, the motor will respond properly. The robot will respond properly to changes in the input command. But if you now start to increase the operating input frequency, then the maximum displacement and the maximum speed of that robot will start to decrease fast to a point where it's simply vibrating and not providing any useful displacement or speed. And the same can be said for electrical components. Especially for those that need to operate at a high frequencies, you always see a Bode plot. That Bode plot tells you or gives you an idea in which frequency range you should operate that system. Of course, you can always increase the input magnitude in order to get a larger output, but there's also limits to that. At one point, we'll reach a physical limit and the output of that system becomes so small that it's not useful. And that's why a Bode plot is very important. It has applications everywhere in electromechanical systems design.
This is the second lecture on Bode plots. In this lecture, we are going to expand on the concepts we introduced in lecture 16 and look at more complex cases of Bode plots. By the end of this lecture, you should be able to represent the magnitude and phase of a Bode plot and draw the Bode plot for functions having complex poles or zeros. Before we expand on the concept of a Bode plot, let's do a quick review of what we learned in lecture 16. The Bode plot is a representation of the frequency response of a given system when subjected to a sinusoidal input signal. In this example, we have a process G of S that is subjected to an input U of S, which is a sinusoidal waveform, and the output of the system is Y of S. If the magnitude of the sinusoidal waveform at the input is A, we know that the output Y of t of this system can be written in the following form: A times M sine of omega t plus phi, where omega 0 is the frequency of the input signal, A is the magnitude of the input signal, and M is the magnitude of the transfer function G of S at this specific frequency. The magnitude of the transfer function is frequency dependent and can be calculated by finding the real and imaginary part of the function G of S when subjected to that particular frequency. The transfer function is then represented as a vector, and the magnitude of that vector on the S-plane is the magnitude of the transfer function. That is, the real part of the transfer function is squared at that specific frequency, plus the imaginary part of the transfer function is squared, the square root of it. And that is the magnitude m of the transfer function at frequency omega 0. The phase shift phi, or the phase of the transfer function, can be calculated by again finding the real and imaginary part of the transfer function and taking the inverse tangent of the imaginary part divided by the real part. This is also frequency dependent. In summary, when we find the real and imaginary part of the transfer function, we can plot that on the S-plane. This distance is the magnitude of the transfer function, and this angle is the phase of the transfer function, which, as we see in equation 1, will affect the temporal response of the system when subjected to a sinusoidal waveform of frequency omega 0 and magnitude A. The Bode plot is a representation of the frequency response of the system as the frequency changed from close to 0 to infinity. We can now take the magnitude of Gj omega, and omega is now changing. Calculate the magnitude of the transfer function, plot that on top of the Bode plot, that's the gain of the transfer function, find the phase of Gj omega at that specific frequency, and plot on the second graph. It is important to note that on a Bode plot, the magnitude is given in decibels. So instead of plotting the magnitude of gj omega, we plot the magnitude of 20 times log 10 of gj omega. And the phase of the transfer function is typically displayed in degrees. Notice also that the frequency axis is also given in a log scale. One of the key advantages of using a logarithmic scale to draw the Bode plot is that the Bode plot can be decomposed into smaller functions, and you can then add them up. To see this, consider the transfer function given in 2. This is simply a gain times a fraction of poles and zeros multiplied together. The Bode plot is given as 20 log of the magnitude of g of j omega, as we see in equation 3. We know that a log of ab equals to log of a plus log of b. Log of 1 over a equals to log of a minus 1, which is negative log of a. This allows us to expand equation 3 as a sum of different building blocks for a Bode plot. We can take, for example, the constant gain and write that part as 20 log of k. We can take all zeros and write that as 20 log of each zero. So create one Bode plot for each zero on the transfer function. And we can do the same for all poles in the transfer function. Thus, if we know the Bode plot of basic functions, we can easily sketch the Bode plot of the combination of these basic functions, that is the Bode plot of g of s. For the phase, we can take a similar approach. If you take the same transfer function, now given in equation 5, we can now calculate the phase of each pole and zero, add the phase of all zeros, subtract the phase of all poles, and that is the phase of the entire transfer function at a particular frequency. We can now define elementary building blocks that will help us construct the Bode plot of complex functions. The first building block is a constant gain, and that is the most simple one, because you know that a constant gain simply results in a constant line on the Bode plot, on a flat line. If you have a gain of k, the magnitude on the Bode plot is simply 20 log of k for all frequencies. And the phase of a constant gain is 0. The imaginary part doesn't exist, so we have a phase of 0 if k is positive and a phase of negative 180 degrees if the gain is negative. This is explained in lecture 16 in more detail. The second elementary building block is the pole at the origin. A pole at the origin implies that the transfer function is 1 over s or 1 over j omega. If you multiply this equation by j and divide it by j, we get negative j times 1 over omega. When you now plot the magnitude and phase of the transfer function, we see that we are on the negative imaginary axis, and the phase of the transfer function is always negative 90 degrees. So a pole at the origin always adds negative 90 degrees to the phase of the transfer function. If you go back to the definition, we have 1 over j omega. The magnitude of this transfer function is simply 1 over omega. If you now take 20 log of 1 over omega, this gives negative 20 log of omega, which corresponds to a slope of negative 20 decibels per decade. By decade, we mean a shift in the frequency by a factor of 10. So if you are at a frequency of, say here, 10 to the power of minus 1, which is 0.1, and we go to 10 to the power of 0, which is 1 radians per second, this is 1 decade increase in the frequency. We notice that the Bode plot will go from 20 decibels to 0 decibels, so it goes down by negative 20 dB. In summary, a pole at the origin results in an angle of negative 90 degrees added to the phase of the transfer function, and a slope of negative 20 log of omega, the frequency, for all frequencies. The third elementary building block is the zero at the origin. In this case, our transfer function is defined as g of s equals to s, or g of j omega equals to j omega. If you plot this transfer function on the real and imaginary axis, we see that we are placed this time on the positive side of the imaginary axis, so the angle of the transfer function is always positive 90 degrees. The phase will then look like this, a constant value of 90 degrees for all frequencies. If you take the magnitude of this transfer function, the magnitude is simply 20 log of s or 20 log of omega, and this now results in a positive slope of 20 decibels per decade. If the frequency is increased by a factor of 10, that is 1 decade, the Bode plot goes up by 20 decibels. Notice that for the pole, we had negative 90 degrees and negative 20 log of omega. For the zero, we have positive 90 degrees for the phase and positive 20 log of omega for the magnitude. The negative of a pole at the origin is the zero at the origin. The fourth elementary building block is a real pole, represented in the following form, where omega 0 in this case is called the cutoff frequency of that pole. Notice the standard form is different from what we used in the other lecture. In this case, we have 1 divided by s over its cutoff frequency plus 1. This is to eliminate any gains in the transfer function so that this elementary building block only manifests the effect of a real pole in the transfer function's gain and magnitude of the phase. The analysis of a real pole is a little bit more complicated, but is still relatively straightforward to understand. We need to distinguish 3 cases. The first case is when the frequency of excitation, the input frequency omega, is much smaller than omega 0, the cutoff frequency of that pole. We saw that when that condition is respected, the gain is 0 and the phase is 0. The second case we need to consider is when the frequency at the input is exactly the cutoff frequency of that pole. The gain becomes negative 3 decibels and the phase now goes to negative 45 degrees. The third and final case corresponds to the case where the input frequency is much greater than the cutoff frequency of the pole. And in that case, we know that the gain now follows a slope of negative 20 decibels per decade past the cutoff frequency, and the phase now tends to negative 90 degrees. In summary, if you look at this Bode plot here for a real pole, we see our cutoff frequency there. The magnitude of the Bode plot is 0 up to the cutoff frequency, then it's negative 3 decibels at the cutoff frequency, and past that point it goes down on a slope of negative 20 decibels per decade. The phase starts at 0, passes at negative 45 degrees at the cutoff frequency omega 0, and then tends to negative 90 degrees. The last building block that we addressed in the previous lecture is the real 0. The real 0 is given as s over omega 0 plus 1, where again omega 0 is the cutoff frequency of the 0. We notice a very similar trend as the pole. Before the cutoff frequency, the phase is 0 and the gain of the transfer function is also 0. At the cutoff frequency, the phase is 45 degrees, positive 45 degrees, and the gain now goes to positive 3 decibels. And past the cutoff frequency, when the excitation input is much greater than the cutoff frequency, the phase tends to 90 degrees and the magnitude of the Bode plot now goes up following a slope of 20 decibels per decade. This is exactly the negative of a real pole on the Bode plot. This is explained in details in lecture 16. If you look at a Bode plot for a real 0, you see that the magnitude goes from 0 up to 3 degrees at the cutoff frequency and then goes up following a slope of positive 20 dB per decade. The phase goes to 0 to 90 degrees, passing at plus 45 degrees at the cutoff frequency. This is what we covered in lecture 16. Here we are going to introduce complex poles and complex zeros as the final building blocks for Bode plot. Before we do that, let's cover one more exercise using real poles and zeros.
In this example, we are drawing the Bode plot of function g of s. In this function, we can identify 3 main building blocks. The first one is the 0 at negative 10, so a real 0. The second is the pole at negative 1. We have 2 poles at negative 1. And the third one is the other pole at negative 100, which means that I have 3 cutoff frequencies, 1 radians per second for these 2 poles, 10 radians per second for this 0, and 100 for the other pole. So here we have the original function, and here is the function written in the standard form we need for Bode plot. Looking at very low frequencies, to the left of all cutoff frequencies, the only thing acting on the Bode plot is the gain 0.1. So the gain at very low frequencies would be 20 log of 0.1, which is negative 20 dB. So the gain is negative 20 decibels up to the first cutoff frequency, which is 1 radians per second. So from 0.1 to 1, we have negative 20 dB. At 1 radians per second, we encounter the first cutoff frequency, which is due to these 2 poles at negative 1. Each pole adds a slope of negative 20 decibels per decade. So the total slope now is negative 40 decibels per decade. And this will go on up to the next cutoff frequency, which will be 10. Now from 1 to 10, we have these 2 poles. The slope becomes negative 40 dB, which means that if you move the frequency by 10, by a factor of 10, the Bode plot goes down by 40 dB. So we should be at around negative 60 dB. Because the slope here is negative 40 decibels per decade due to these 2 poles at negative 1. When you now reach 10 radians per second, we have a 0. The 0 adds plus 20 dB per decade. It will add plus 20 dB to a existing slope of negative 40 dB. It doesn't make the slope 20 decibels per decade. It adds 20 decibels per decade to the slope immediately before it, which means that now the slope becomes negative 20 dB. So we are at here 60, negative 60 dB. If you go from 10 to 100, that is a factor of 10 in the frequency, the Bode plot goes down by 20 dB. So now the slope becomes negative 20 decibels per decade. Here we were at negative 60, so here we are now at negative 80 decibels. When you reach now 100 radians per second, we have another pole. So the pole adds negative 20 dB to this slope, which means that things will now go down again by negative 40 dB per decade. Negative 20 plus additional pole, negative 20, negative 40. So from 100 to 1000, the Bode plot needs to go down by another 40 dB. So the slope becomes negative 40. Here we are at negative 80. We go down by negative 40. Here we have negative 100 dB at 1000 radians per second. Now, of course, here we neglected the 3 dB at each cutoff frequency. In reality, the magnitude here should have been negative 23 dB if you had one pole at negative 1. So negative 20 plus minus 3 at the cutoff frequency. But because you have two poles, this should be negative 26 dB. Negative 3 for each. When you get to 10, 10 adds 3 dB above the current value, so we would have negative 66 up to this point, plus 3 from the 0 would be negative 63 dB. And here at 100, we have negative 83. Would have negative 63 minus 20, that would be negative 83. Minus the 3 dB from this pole would be negative 86 decibels. And of course, at 1000 radians per second, we would be at a negative 126 dB. Now let's look at the phase. If you go to the left of all cutoff frequencies, we don't have any poles or zeros at the origin. We only have this gain acting on the Bode plot. So it is easy to say that the phase at very low frequencies is 0. It is 0 up to the first cutoff frequency. The first cutoff frequency comes from these two poles at negative 1. Each adds negative 90 degrees to the phase. So the phase goes down by 180 degrees, 90 for each pole. And this stays at negative 180 up to the next cutoff frequency at 10. This is a 0. The 0 adds 90 degrees, so we go up to 90 degrees, negative 90 degrees. And this stays at that value up to the next cutoff frequency, 100. Another pole, another negative 90 degrees, so we go from negative 90 back to 100, negative 180. If you now interpolate to this curve, you should get something like this. Passing here by negative 90 degrees, halfway. Passing here by negative 135, if I had done this properly. And here is negative 135 as well. So here we have the phase, and here we have the magnitude of the function g of s.
Now let's expand on the comp set and include the complex conjugate poles and complex conjugate zeros to our Bode plots. You only get complex conjugate poles when you have a second order transfer function, and the standard form for a second order transfer function is given here. We again want to isolate the effect of a pole in this Bode plot, so we have to eliminate the effects of gains. That's why we need to now normalize this transfer function with respect to omega 0 squared. If you divide the top and the bottom of this equation by omega 0 squared, we have 1 over s squared divided by omega 0 squared plus 2 zeta omega 0 over omega 0 squared times s plus 1. The first term here can be rearranged as s over omega 0 all squared, and this omega 0 will cancel with the square here, so this becomes 2 zeta s over omega 0, plus 1, of course. Here we now have the standard form of a second-order transfer function for Bode plot. We have 1 on the numerator and 1 in the denominator here, so the gain, the DC gain of this transfer function is 1. The next step is to find the real and imaginary part of this transfer function. To do that, we can now replace s with j omega. The first term here becomes j omega over omega 0 all squared. J squared is negative 1, so you have negative omega over omega 0 squared. The second term simply becomes j omega, and the last term is not affected. After this manipulation, we can clearly see the real part of the denominator and the imaginary part of the denominator. The next step is to now eliminate the complex conjugate from the denominator. To do that, we need to multiply the transfer function by its complex conjugate, which means that if this is the real part and this is the imaginary part, we can simply multiply the numerator and the denominator by the complex conjugate of that. The conjugate of that is simply this minus the imaginary part, negative j minus 2j zeta times omega divided by omega 0. Recall again that omega now is the input frequency to the system. The advantage of this method is that now in the denominator we have a plus b times a minus b, which results in a squared minus b squared. So for b we get negative j2 zeta omega over omega n squared. J squared is negative 1, so this becomes now positive 2 zeta omega over omega 0 all squared. And that's the term we see here. Now through this manipulation, we have no more complex numbers in the denominator of the transfer function. Instead, if you now expand the numerator of the calculation we did in equation 9, we can now clearly see the entire real part of the transfer function and the entire imaginary part of that same transfer function. And this is what we need for the next step in order to find the phase and the magnitude of the transfer function. So here again we have the same function, the real and imaginary part are shown. Up to this point, this is the same procedure we use to define the phase and magnitude of real poles and zeros. Now to analyze the phase and magnitude of this building block, again we have to consider three cases. The first case is when the input frequency omega is much smaller than the cutoff frequency of the complex pole. In this case, you can assume that omega divided by omega 0 tends to 0, which will make this term 0, this term 0, this term 0, 0, 0, and 0. What is left? We have 1 from the real part and the imaginary part is 0. So the transfer function now simplifies to 1 plus 0j. If we plot this on the real and imaginary axis, we have 1 for the real part, 0 for the imaginary part. Clearly, the phase is 0 degrees. And the gain of the transfer function is this distance, which is 1. So in decibels, that is 20 log of 1, or 20 log of the square root of the real part squared plus the imaginary part squared, which is 1. And this is 20 log of 1 is 0. Here we get the same conclusion we had for the real pole. Up to the cutoff frequency omega 0, the gain in the Bode plot is 0 decibels. For the magnitude, the transfer function is 1 in non-decibel scale. The phase is also 0. And this holds up to the cutoff frequency. So up to this point, this is equivalent to the real pole. In the second case, now we're going to consider the case where the input frequency is much greater than the cutoff frequency of the pole. In this case, you can assume that 1 minus omega over omega 0 squared is approximately omega over omega 0 squared. So this number 1 here can be neglected, this number 1 here can also be neglected, and so on. Through this manipulation, we can now further simplify both the real and imaginary parts. I'm going to skip that, but it's a relatively simple process. And after the simplification, under again the assumption that the input frequency is much higher than the cutoff frequency, the transfer function simplifies to this, where we see the real part and we also see the imaginary part here. What is the gain of this transfer function in decibels? Well, that is simply 20 log of the real part squared plus the imaginary part squared, square root of that. This is what we see here. We can notice that the second term in this expression, this one, is to the power of negative 6. whereas this term is to the power of negative 4. Thus this term can be neglected compared to the first one. And if that is the case, now we can simplify the square with the square root. So this term, second term, goes to 0. The square root and that term will cancel out. But also remember that when we square this part here, this negative sign goes away. So we are simply left with 20 log of omega divided by omega 0 to the power of negative 2. So this negative 2 can move to the front, and here we have the final magnitude. Negative 40 log of omega divided by omega 0. If you recall, for the real pole, we had the negative 20 log of omega over omega 0. For the complex pole, we have negative 40 log of omega divided by omega 0. So this is equivalent to having two poles, two real poles. This creates a slope of negative 40 decibels per decade past the cutoff frequency. This is easy to see. If our cutoff frequency is omega 0 right here, we have negative 40 log of omega divided by omega 0. If they match, if omega equals to omega 0, this is 0. If omega is 10 times omega 0, this is negative 40 log of 10, which is negative 40. If omega is 100 times omega 0, this will be negative 40 log of 100, which is negative 80 decibels, and so on. So as the frequency increases by a factor of 10 past the cutoff frequency, the Bode plot now goes down by negative 40 decibels. This adds a slope of negative 40 decibels per decade past the cutoff frequency. Now let's look at the phase. Still, when the input frequency is much greater than the cutoff frequency, we can simplify the transfer function to this. Now the phase of the transfer function is relatively easy to calculate. It's simply the inverse tangent of the imaginary part divided by the real part. And after some straightforward manipulation, we get here. We know that omega is much greater than omega 0, which means that this term will tend to 0. Thus the phase of the transfer function tends to negative 180 degrees. Wait, what is this 180 degrees and not 0? Now let's go back to our transfer function here and plot that. We see that both the real and imaginary part are negative. So our point that represents the transfer function at that particular frequency is in the third quadrant. As the frequency increases and the magnitude of the transfer function tends to 0, as we saw before, it does so in the third quadrant, which means that the phase will tend to negative 180 degrees and not 0. Remember that when you had a real pole, the phase was negative 90 degrees past the cutoff frequency. Now for a complex pole, the phase tends to negative 180 degrees. Again, we have the same effect of having two real poles at the same cutoff frequency. Up to the cutoff frequency, both the phase and the magnitude are 0. Past the cutoff frequency, the magnitude decays by negative 40 decibels per decade, and the phase tends to negative 180 degrees. This would be equivalent of having two poles, two real poles with the same cutoff frequency. The only difference occurs at the cutoff frequency exactly, and that's the next case we are going to see. Now back to our original transfer function, here it is. Now let's consider the case where the input frequency is exactly the cutoff frequency of that complex pole, so omega equals to omega 0. This is a very simple case to deal with because the entire first term tends to 0 straight away. If you look at the numerator, we see that if omega and omega 0 are the same, the entire real part tends to 0. And the imaginary part simply simplifies to negative j times 1 over 2 zeta. This is now our transfer function. If you want to find it again you need to do real part to square plus imaginary part to square root of that, and here it is. Real part in this case is 0. The square root and this square will cancel out, they bring with them the negative sign, and this simplifies to 20 log of 2 zeta to the power of negative 1. So negative 1 can go to the front of the log, and the final magnitude of the transfer function is negative 20 log of 2 zeta. And this is a very interesting result. Now the magnitude of the transfer function at the cutoff frequency depends on the damping ratio. If the damping ratio is exactly 0.5, then you have negative 20 log of 2 times 0.5, which is 1, and log of 1 is 0. In the second case, the damping ratio is assumed to be smaller than 0.5. If that is the case, 2 times a number that is smaller than 0.5 is smaller than 1. So log that a number that is smaller than 1 results in a negative number. This negative number multiplied by that negative number becomes positive, which means that if the complex pole has a damping ratio of less than 0.5, then the magnitude of the transfer function at the cutoff frequency will increase by a certain factor. It will peak at the cutoff frequency. It will go up. If the damping ratio is greater than 0.5, however, then we have the opposite. This would result in a number that is greater than 1, which means the log of that number will be a positive number. This positive number multiplied by the negative sign becomes a negative number, and now we have a negative gain at the cutoff frequency. So if the damping ratio is greater than 0.5, then the Bode plot goes down by a certain amount at the cutoff frequency. When the damping ratio tends to 0, the negative 20 log of a number that tends to 0 will tend to infinity. The last thing we need to deal with is the phase at the cutoff frequency. At the cutoff frequency, again, omega equals to omega 0. Here we have the real and we have the imaginary part. We can simply do the imaginary part divided by the real part, which is 0. So we replace that with a constant c and make c tend to 0. This will give a phase of negative 90 degrees at the cutoff frequency. And here is the summary for the complex pole. When the input frequency is smaller than the cutoff frequency, the gain is 0 and the phase is 0. When the input frequency is much greater than the cutoff frequency, then the Bode plot has a slope of negative 40 decibels per decade and the phase will tend to negative 180 degrees. At the cutoff frequency, when omega equals to omega 0, this should all be omega 0 instead of omega n, then the gain of the transfer function is negative 20 log of 2 zeta. So now depending on the value of zeta, the Bode plot may go up or down at the cutoff frequency. And at that specific point, the phase is negative 90 degrees. Notice that this is analogous to having two equal real poles at the same cutoff frequency, with the exception of what occurs exactly at the cutoff frequency. Now the Bode plot may go up or down depending on the value of zeta. Now let's plot a sketch of the complex pole on the Bode plot. Here our frequency is omega 0. That's the cutoff frequency of the complex pole. Up to omega 0, we have a slope of 0 on the Bode plot. That is at 0 actually. Past the cutoff frequency, we go down by negative 40 decibels per decade. The phase goes from 0 to negative 180 degrees. Of course, this happens with a smooth function, something like that. And what is that window? This window will depend on the cutoff frequency and also depends on the value of zeta. The smaller zeta, the smaller that window. The larger zeta, the larger the window where the phase changed from 0 to negative 180 degrees. But what happens exactly at the cutoff frequency for the phase? To see that, let's consider this function 1 over s squared plus 2 zeta s plus 1. And here we have our damping ratio zeta. Let's change zeta from 0.1 to 0.9 and see what happens. We see that when zeta is smaller than 0.5, which will occur for these curves, now the Bode plot goes up. This means that the magnitude of the output of the system will increase. If zeta now becomes greater than 0.5, then the magnitude will now decrease, and this is what occurs for these remaining functions. Notice how the phase behaves. When zeta tends to 0, the phase goes from 0 to negative 180 degrees rapidly, but it will take much longer when now the damping ratio tends to 1. What happens when zeta is greater than 1? Well, then you don't have complex conjugate poles, we have two real poles. Once again, we notice that this is very similar to having two real poles at the same cutoff frequency, because the magnitude goes from a slope of 0 to a slope of negative 40 decibels per decade past the cutoff frequency, and the phase goes from 0 to negative 180 degrees. The difference occurs at the cutoff frequency. Now, you remember the example we had in lecture 16, where a bridge collapsed because it was excited by a wind having a particular frequency. It turns out the wind frequency was very close to the cutoff frequency of the transfer function of that bridge. And probably because of a poor design, the bridge had a transfer function with a damping ratio of less than 0.5, which means that when wind hit the bridge at the specific cutoff frequency, the magnitude of the oscillations were at the maximum. And that's what made the bridge collapse. It makes perfect sense. A way to stabilize that bridge would be to add dampers somewhere in the structure. When we add dampers, then the damping ratio goes up. There is something dissipating energy. If the damping ratio now goes up and is greater than 0.5, then we see that the Bode plot goes from going up at the cutoff frequency magnitude to going down, to have a negative gain. And this would have avoided the large displacement magnitudes of the bridge when the wind hit the bridge at the cutoff frequency. Something that you have to notice is that the maximum gain of the transfer function doesn't necessarily occur at the cutoff frequency. It is very close, but it's not necessarily the cutoff frequency. The point on the Bode plot that results in the maximum gain is called the resonance frequency. The resonance frequency satisfies the maximum of the gain function. To find the resonance frequency, we can take the magnitude of the transfer function, take the derivative with respect to frequency, and set that to 0. We can now solve for omega, and the value of omega that satisfies this expression is omega r, the resonance frequency. And you can find it through some manipulations that I'm going to skip in this lecture, but the result is shown here. We see the cutoff frequency of the complex pole, and we see that it is multiplied by this constant that depends on the damping ratio. So the damping ratio, or zeta, will shift the cutoff frequency and the resonance frequency by a certain amount. They are very close, but they are not necessarily the same. If you now take omega r and input that back into this big function and find the magnitude, we see that the magnitude at the resonance frequency is given here. It is only a function of the damping ratio. Now let's go to the light board and solve some more exercises. Thank you.